Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to look at finding numerical approximations to systems of first-order initial value problems and higher-order initial value problems. So up until now in these labs, we've been looking at how do we approximate solutions to first-order initial value problems. We're now going to take one step further, and we're going to see how we can approximate solutions to systems of first-order initial value problems, as well as looking at higher-order initial value problems, and specifically we'll see systems of second-order initial value problems. So by the end of this lab, you're going to be able to understand how to approximate the solution to a system of n coupled initial value problems. You will understand how to reformulate an nth order initial value problem as a system of n coupled initial value problems. You will also understand how to reformulate a system of n second order initial value problems as a system of 2n first order initial value problems. So what is a system of ODEs? Well, here we have n different ordinary differential equations where the derivative of the first function depends not only on t and its value, but also on the value of all the other functions. Similarly, every other function, its derivative also depends not only on t and the value of the function, but the value of all the other functions. So here's an example. Here's a very simple second system of two coupled ODEs. The first one tells us how many rabbit families there are per acre, R of t. The second gives us the number of fox families per acre, F of t. Now, this represents the rate of growth of a predator and a prey in a natural system. So now, rabbits are going to increase exponentially as long as there aren't too many foxes. So again, the rate of growth of rabbits is going to be growing exponentially as long as the density of foxes is less than 0.5 families per acre. Similarly, the foxes will grow exponentially as long as there are sufficient rabbits to feed them. So as long as the rabbit population is greater than 1, the fox population is going to grow exponentially in a positive direction. In the opposite case, you're going to have exponential decay. Now, these are coupled, so as the rabbits grow, the foxes grow. But as the foxes grow, they start to eat more and more rabbits, and so therefore the density of rabbits starts to shrink ever faster. So how do the two actually interact? Well, suppose that the initial state is we have a fox density of 0.3 families per acre, a rabbit density of 0.5, and these are our initial conditions. Now, initially, 1 minus 2 times 0.3 is 0.4, so the rate of growth of the rabbits will be increasing. The fox population, however, will be decreasing. Now, there's no way to actually find exact solutions to these ODEs, so if you actually want to experience this, we have to approximate the system numerically. So for example, you can actually set up this system in Maple. You can ask it to solve it, give it the two initial conditions, state the two ODEs. It will not be able to find a numeric approximation. But solving it numerically, we notice that, as expected, we have growth of rabbits, but the growth of rabbits also results in a growth of foxes. As the growth of foxes gets too large, the rabbits start to get eaten, and so they diminish in population. As there are fewer rabbits to eat, the number of foxes also decreases. And then it cycles again. With fewer foxes around, the rabbits have the opportunity to grow again. This is a plot of both the rabbits and the foxes per acre. So we can also plot this as a function of time of foxes versus rabbits. Initially, the number of rabbits begins to increase while the number of foxes decreases. As the number of rabbits increases, so do the foxes. But as the foxes are increasing, well, then the number of rabbits decreases, and we cycle around and around. And so ultimately the system continues to cycle forever. Now, of course, in reality, foxes and rabbits, there are many other factors that we're ignoring right now. But as a simple model, it works. Here's another system of equations. Lorenz, when he came up with these many years ago, found that he could couple various relationships or rates of change in the atmosphere based on these equations. And so here we have n is equal to three coupled equations. X of t, y of t, and z of t. What these actually represent, you can look up if you wish. Now, these are atmospheric conditions. These are the actual relationships that he found. And both x, y, and all three of x, y, and z are functions of time. And again, here we also do not have a general solution. As before, we need to know the state of the atmosphere at some initial time. So we know that at time t0 we have three initial values. Now, if the values of sigma, beta, and rho are all 1, what happens is that the system converges from any initial point to the origin. No matter where you start, if we start at 1, 1, 1, over time, all three functions x, y, and z converge to 0. If, however, we let beta is equal to -1, then we get a different response. In that case, x and y go to 0, but z goes to positive infinity. And so you get a spiraling around the z-axis to infinity. Again, it doesn't matter where we start. Here I'm starting at 1, 1, 1, but most points will diverge. Now, here's an interesting scenario. If I let sigma is equal to 10, rho is equal to 99.96, and beta is equal to 8/3, then the system does not converge nor diverge, but it has a limit cycle. So over time, no matter where you start, it's going to start moving around, and ultimately it will follow this limit cycle. So no matter what happens, you will always converge towards and closer to this limit cycle. Now that's called an attractor. What Lorenz, however, found was there's also special cases where we get very bizarre results. So if we take a look at sigma is equal to 10, rho is equal to 28, and beta is equal to 8/3, the solutions, the values of x, y, and z always remain bounded, but there's no limit cycle. So we start here, and we start rotating around. X, y, and z are changing, and then we jump over to here, and then we jump back. And forever, we're cycling around and around. Now, this is the actual graph from which the description of the butterfly effect comes from. Any small change in initial conditions will ultimately change how often the solutions jump back and forth between these two states. So that is called a strange attractor. It doesn't converge to it, doesn't diverge. Now, you don't have to know this terminology, but it's sort of interesting to see what can happen when you start having systems of coupled ODEs. So how are we going to solve this? Well, let's first take our system of ODEs, and let's start by defining a vector-valued function. And the vector-valued function y just takes each of the n functions, y sub 1, y sub 2, y sub n, as its entries. So now we have a vector-valued function y of t. Okay, so that's what we're taking. Now we take the system of differential equations, and we can now write all of this, the second through the nth plus first terms. We can just write that as a second argument. And so now if we're referring to this entry, we would just refer to the second entry of the vector valued function y. Now we can define a vector valued function of the system of these functions. So now bold-faced f, the vector valued function f, takes this, returns this, given t and y of t in its first component, and returns this value here, for example, in the last entry or last component of that vector. But if we now have y is equal to that vector, then let's say we differentiate y. Well, how do we differentiate a vector? Well, we differentiate each term. So if we differentiate this vector valued function, we just differentiate each of the terms. How are each of the terms changing? Well, wait a second. The derivative of y1 is just f1. The derivative of y2 is just f2. And this expression here is just our vector valued function f. All right, so far so good. So in our two examples, we could have, here's our rabbit and fox population. The rate of change of the vector values is the first component times twice 1 minus twice the second component, y2. The rate of change of the second function is the second component, f, times the first component, r of t, minus 1. So here, y is not just a scalar, but it's a column vector of 2 dimensions. In the second example, in the Lorenz equations, here's our constants. We're going to define them a priori. And now, sigma times the second component minus the first component. The derivative of the second function is just the first component, or the first function, times rho minus the third function, all minus the second function. And similar for the third one. So in this case, the second argument is not going to be a scalar, but it's going to be a 3-dimensional column vector. Now, as well, we need initial conditions. We need to know what the initial state is of each of the functions. Well, that's just going to be a vector of values. So let's call that y sub naught. And it's a vector of n values. So in our two examples, the initial state could have been 3/10 and 1/2, or in our second example, in the Lorenz, the initial state would have been 3 vectors, or a vector of 3 values, 1, 1, 1. Okay, so now let's take a look at what we were looking at previously. Here we have a single ODE, and here we have a coupled system of n ODEs. But notice we're just using vector notation. So if we're just using vector notation, how do we approximate this? Well, let's recall, how did we approximate a single ODE? Well, we took approximation into the future is the previous value plus h times the slope. Well, is it any different for this? What is the value of this vector in the future if it is anything but the value of the previous plus h times the vector of the slopes at that initial value, at t naught? So it looks a lot like a vector plus a scalar times a vector, which gives us the approximation at the next step. In fact, that's exactly what we're doing. Now, if f is returning a vector of 2 values, well, here we have a vector, y will be 2 values because the output will be 2 separate values. Here we have vector multiplication and vector addition. Sorry, scalar multiplication, vector addition. We've calculated 2 vectors. So both of these are vectors containing the slopes. Here I'm adding 2 vectors and then multiplying them by h over 2. So we have vector addition plus scalar multiplication. So we don't really have to do anything for, in this example, Heun's method to make it work for systems of ODEs. Well, almost. We just have to worry about the output vector. The output vector is no longer a vector, but now a matrix. So you'll remember that using Heun's method initially, we started off by setting up the values and then calculating them, at least for the adaptive. In the adaptive approach, of course, the difference between the t's could change. What we're going to do now, instead, is we're going to have an initial state, so the value of the first function is 1, the value of the second function is 2, and now over time, both of these will move and change over time. Does this make even sense? Well, let's take a look. I'm claiming, well, this is for the rabbits. So you can see how the populations will change over time. So in many cases, we can use all the same code. We just have to make a few small checks and balances. So first of all, we have to make sure that the initial vector y0, it's no longer a scalar, but it's now going to be an n-dimensional column vector. So let's get the size, and let's also get the second size as well. Now the second size had better be 1, so it better be a column vector. So the number of columns is 1. So we'll check that. If it's not equal to 1, we'll throw an exception. Just give the user a warning. Hey, the initial conditions did not satisfy, well, are not a column vector. Now, the output is no longer going to be an array of zeros, but instead, well, sorry, for Heun's method, the output would be a matrix of n by n entries. So 2 by n entries, and the first column is going to be our initial condition, and then we'll just keep on updating them. That's if we use Heun's method, where we know a priori how many points we're dividing the interval t0 to t final into. Assignment is a little bit more difficult, because now we can no longer refer to just the kth entry in the output function, but we have to make sure that we are referring to the column, the kth column in that, and we're also assigning to the kth column, or kth plus first column in this case. So we are now going to have to refer to columns within the output, at least again for Heun's method. If we're looking at the adaptive Euler-Heun method, again, what do we have to change? We have to make sure that we're referring to the columns in the output vector. But there's only one other additional thing we have to do. What's that term there? The absolute value of a vector. So we can't calculate the absolute value of the difference between two vectors, because the absolute value is only that of a complex number. Now, if, however, both y and z are approximating the system at time t out k plus 1, then basically both those vectors are approximating vectors that should be about the same value. Now, if two vectors are close, then the norm of the difference of those two vectors is small. So therefore, assuming we want to approximate the solution to some final value epsilon abs, then rather than using the absolute value of the difference between y and z, let's use the norm of the difference between y and z. How close are those two? Y is a fourth order approximation, z is a fifth order approximation. How close are those two? We'll use that to calculate S. The last step for Dormand Prince that we have to modify is, once again, we get the size, and in this case we're going to make sure that the number of columns in this initial condition is 1, otherwise we throw an exception, and now y sub out is initialized to the initial value. So now y out begins as just a column vector. And then we will assign to the next column, which will expand the matrix, and so on and so forth. Finally, we're no longer going to be calculating just a vector of k values. Remember, before we calculated 7 different values of k. Now we're going to be calculating 7 different values for each of the n functions. So now, the first time we iterate through this loop, we will assign to the first column for each of the n entries, each of the n slopes. Then we will assign each of the capital N slopes to the second column, the third column, all the way up to the n sub kth column, which in this case is equal to 7. After that, we can do the exact same thing. Once again, we don't have to do anything else to modify this, because now we are going to approximate those slopes, times them by our coefficients, multiply them by h, and we're done. So we've determined the scaling factor as before, we've used the norm, and now we're assigning to the output vector, but again we must assign to the kth plus first column of the output. And again, this works just as before. If we have a vector of entries 1 and 2, if I assign to the second column 3 and 4, it just extends the size of the matrix. If I assign to the third column 5, 6, it again extends. And the fourth column extends it to 7, 8, and we're done. So looking at the rabbit and fox problem as before, letting it run for one time interval with the initial conditions we stated before, it iterates nicely, and we get both the population of the foxes, the population of the rabbits in the first column over time, and the population of the foxes over time. So initially, the rabbits are increasing. Initially, the fox population is decreasing. If you want to try this example out just to make sure that your code is working, here is the matrix of k values that you should be calculating at time t1 is equal to 0, our initial t value. Remember, our t interval is from t naught to t final, and in Matlab we have only integer values from 1 on for entries. So t1, the first entry of the t output vector, is the initial time, t naught. So t1 is equal to 0, h is equal to 0.1. We've calculated that. We've calculated our approximate values. Notice that they're reasonably close. And when we calculate s, s is equal to 4 and change. That means that we can double h for the next interval. All right, second interval. We want to calculate, so t2 is equal to 0.1, h is equal to 0.2, therefore we're going to be approximating the result at t is equal to 0.3. Here's our matrix of slopes. Here we have our two approximate values. When we consider the difference, when we calculate s, we get a value of 2.55 and change. So once again, we should double the value of h for the next interval. So now h is equal to 0.4. h is equal to 0.4. We are at t3 is equal to 0.3. Our next approximation will be at t4 is equal to 0.7. These are the slopes. These are our approximations. And again, as we can see, the rabbit population seems to be positive. The fox population seems to be decreasing. Here are two approximations, and s is now equal to 1.7. Now 1.7 means that we're not going to double the value of h, and neither will we reduce the value of h. Recall, however, that we are going from 0 to 1 for this small example, and so even though we're leaving h unchanged, 0.7 plus 0.4 is 1.1. That's beyond our endpoint. So instead, we will update h and let h is equal to 0.3, the difference. So at the end, we're at T4 is equal to 0.7, h is equal to 0.3. We're approximating the solution at the next point. Here's our k values, here's our approximations. S, well, we don't care about S anymore because we've reached the final endpoint and we have our solution or our approximation. You can do this yourself. Here's something. We're going from time t equals 0 to time t equals 6.66. Notice that this gives us almost exactly one full loop. So the period is approximately 6.66 units of time. In this case, we needed 817 points to get the approximation or the precision we were looking for. In this case, let's try it with a Lorenz Attractor. With the Lorenz equations, if we let it run for 10 seconds, we have about 2,318 steps to get an accuracy of 10 to the negative 5. And so we go forward and we cycle around a few times. If you want to try really hard, what we can do, and I rotated this output, so you should rotate yours, going from time t equals 0 to 100 with an error of 10 to the negative 4, we have about 29,000, almost 30,000 points, and when we plot them, we get this beautiful butterfly effect. Now, what do we want to do if we have higher order ODEs? We've looked at approximating systems of coupled initial value problems, and they're all first order, they're all only dealing with the derivatives. What happens if we have the derivative, the fifth derivative, or the seventh derivative of a function is equal or is a function of lower order derivatives? So let's say we have a single nth order ordinary differential equation. Again, from the implicit function theorem, we're guaranteed that almost everywhere we can take almost any nth order ODE and rewrite it in the form that the nth derivative is some function of lower order derivatives, y of t, y prime, all the way up to the nth minus first derivative. All right, great. So we have that form. And we also will need initial values. We need to know what the initial state is. We need to know what the initial slope is. In fact, we will need to know an initial value for each of the first n-1 derivatives as well as the initial value. And all of those are going to be given constants. All of them are given. We would like to see how the system proceeds into the future. Now, how are we going to rewrite an nth order differential equation in terms of first order initial value problems? A system. Well, let's define y of t as just w1. Let's define its slope as w2, the second derivative as w3, the n minus second derivative as an unknown function wn minus 1, and the n minus first derivative will be defined as wn. So now we have this relationship. We have redefined all of these unknown functions and slopes and derivatives, second derivatives, as unknown functions. We can differentiate. So now differentiate each of these terms. Now wait a second. That's equivalent to just differentiating the first function, the second function, the third function. Now, if we take a look at our original definition, what's the derivative? Well, the derivative was defined as w2. What's the third derivative? So, the third derivative is just w3, or sorry, w4. So now, the derivative of W1 is just W2. The derivative of W2 is W3. The derivative of W3 is W4. The derivative of the n minus first W is the last one. There's only one unknown. What is the nth derivative of y? Well, wait a second. The nth derivative of y was given. The nth derivative of y was given by our ODE. And this ODE is just in terms of y, y prime, and all of its lower order derivatives. But we know what these are. We define them as W1, W2, all the way up to Wn. Well, if we define all of these as just vector values, let's just rewrite it as the nth derivative is a function of t and w of t. All right, so now we have that a system, the derivative, is equal to this vector valued function. And the last entry is our ODE in terms of that function. So let's, as an example, let's look at the Euler-Bernoulli beam theory. This says that the fourth derivative is the pressure on the system in that dimension over the elastic modulus and the second moment of area. Again, as long as those two are constant. The equation is slightly more complex if these are also varying over time, or over z. In this case, we have w of z is a sequence of 4 derivatives: v, v prime, v double prime, v triple prime. Therefore, the derivative is just w2, w3, w4, and our right-hand side, the fourth derivative, is just going to be qz over ei. You can then use this, if you use finite elements, to actually model the behavior of a beam when force is placed upon it. Hopefully this isn't the beams used in E5. All right. We also have initial values. The initial value of W1 is just the initial value of the function. The initial value of W2 is just the initial slope, and so on and so forth. Those are exactly what are given in our initial value problem for an nth order initial value problem. So here is our vector of initial values, and we will define that as W0. So suppose we have the following initial value problem with n is equal to 2. The second derivative is a function of the first derivative, the function, and time. Here's our initial value of the function. Here's our initial slope, or rate of change. So therefore, we will define w as a function of as a vector of 2 values. The rate of change, well, the rate of change of w1 is just w2. The rate of change of w2 is this expression here. What is this expression here? Well, it's just negative w2, because w2 is y prime, minus 3 times y, which is w1, plus t minus 1. The initial conditions are 1.2 and 1.3, taken from here. So in Matlab, the initial conditions would be just a column vector of 2 entries, and this function would be defined as f(5c), a function of both time and w. The first entry, the rate of change of the first entry, is just the second entry of this argument. The rate of change of the second function is just negative w2 minus 3 times the first entry, w1, plus t minus 1. And now we can, having modified dp45 previously, all we have to do is pass f(5c), and we get the exact behavior that we want. Is this what we expect? Well, let's take a look. Notice that the rate of change, the initial rate of change is 1.3. But it seems that between 0 and time t is equal to 0.1, the rate of change seems to be dropping to about 0.72. So on average, the slope seems to be about 1 on that interval. Notice that the first entry here changes approximately h times 1. In this case, h is equal to 0.1. This is approximately 0.1 times 1, and so we get exactly that increase. Similarly, here we get an even smaller increase, and now we're getting a decrease. The first row are the values of y of t. The second row are the values of its derivative. Okay, taking a look at these results, here we have the actual function, and here we have the derivative. Notice that right around here, the derivative of this function becomes negative. What's really nice about this problem as well is we can actually find an exact solution in Maple. If we set up this problem in Maple, we get the exact solution here. Having found the exact solution, we can plot it. But not only that, Maple has a code generation package that allows you to translate this equation into Matlab. All right, bonus, we have the Matlab output of the exact solution. We can cut and paste that into Matlab. So I can actually take that and define the exact solution. Now I've cleaned it up slightly, but this is the output from Maple, so I didn't have to do much. I'm just making it look a little bit nicer. We have a constant times an exponential, that's decaying. We have times a sinusoid, that depends on t, times the square root of a value. Exponential, cosine, and then another term that depends on t. So now we can plot both the actual solution we got from Maple and our approximation using dp45 with epsilon step is equal to 10 to the negative 4. And we get what appears to be a really nice approximation. Here you can see that h is smaller. Here h is larger. In fact, as we calculate the difference between the last value and the solution, we get that it's reasonably close. It's definitely within our required error. We can even plot the error directly by taking the values of the function and subtracting off the actual solution at those times. So as we can see on the entire interval, the error does not seem to go outside 3 times 10 to the negative 6. And again, that's exactly what we asked for. We had epsilon abs to be 10 to the negative 4. Here's an RLC circuit. Now, this RLC circuit applying Kcl gives us that expression there. I'm going to substitute the derivative of the charge for I. So here we have the derivative of the current times R for the resistor. Making that substitution, we can simplify this to get L times the second derivative plus R times the derivative of the charge plus 1 over C times the charge. All of that is equal to the forcing function, the voltage input. Now, this is an initial value problem where n is equal to 2. So we can again rewrite this. W is just a function of two values, Q and its derivative current. The derivative of W1 is W2, the derivative of W2 is the right-hand side here. Q prime is W2, Q is W1. The initial values are the initial charge and the initial current. Because the time derivative is a dot, I'm specifically leaving the dot off of the initial current. All right, so in Matlab, we can rewrite this as here's our constants, here's W2 as expected, and again, here we have our input voltage minus the resistance over the inductance times W2 minus 1 over the capacitance and the inductance times W1. And now we can use dp4/5 again as expected. Going from time t equals 0 to 1, we get about 4 steps. In this case, the first row gives you the charge. So what is the change in the charge on the capacitor? And what is the change in the current in the system? Since it's a simple loop, it's just looping through. And that's just Q prime, that's the current. So taking a look at the results on this smaller interval, we see that the charge is initially increasing and then decreasing, but slowly decreasing, so it's concave down. The current is increasing. Now, we can actually solve this system for the current in Maple as well. Plotting it, we get that there is a limiting behavior and it's sinusoidally decaying, approaching it. Maple gives us this as the solution. I can do code generation to give us the output, and I can save the code generated by Maple in a Matlab file. So this is the exact solution, and I can compare the exact solution with what we found with dp4/5. And again, dp4/5 seems to do a reasonably good job on the interval from 0 to 10. How good is the approximation? Well, it's still quite good. Remember that epsilon abs is 10 to the negative 4 in this case, and all of the errors are on the range 10 to the negative 5. So this seems to be reasonably good. Notice here there was a change in H value, and so the error increased, but the error is still less than the maximum we considered acceptable. So that's quite reasonable. Now, let's say instead we have a discontinuous forcing function. We've started with a forcing function that was constant. We saw that the limiting case was a sinusoidal, exponentially decaying approach. What happens if we have a discontinuous forcing function? What happens if the coefficients are time varying? For example, what happens if we have a source that is cut off at time t is equal to 5? Now, this is the unit step function, which you will see in your other courses, but essentially that is going to turn off the system at time t equals 5. In Matlab, we can implement this as time less than 5 times our input voltage. Input voltage is still a constant, so we don't need element-wise multiplication. However, if we now try to approximate it, Matlab seems to go into an infinite loop. Try using Control-C if you try this. What happened here? Well, there's a discontinuity. There's a discontinuity in the input voltage. We switched off the voltage at time t is equal to 5. That means there's also a discontinuity in the derivative. However, the Dormand Prince method, the adaptive method, assumes that the function is continuously differentiable. That means the derivative must be continuous. And so at every single step, it keeps on dividing h smaller and smaller and smaller and smaller, trying to get an accurate answer until h is so small that h plus our previous value is just the same value. We've gone below the threshold that adding h onto the previous value of t, it no longer makes a change. How are we going to fix this? Well, basically, we've calculated y and z, and if adding h over 2 makes no more change to the output value, or the t value, then ignore s. No matter what happens, use the current value of h. Now, another possibility may to have a lower limit rather than just letting h get so small, we may have a lower limit on the value of h, or a relative lower limit on the value of h. In this case, h has got to be approximately 1,000 times larger than the smallest possible value of h that would break or make no change to the time. So now we can solve it. So if you just implement this solution here, if t out sub k plus h over 2 leaves t out k unchanged, then just use the current value of h no matter what. Ignore s. In that case, notice what happens as before, except as we get to the discontinuity, Dormand Prince keeps on refining and shortening the value of h. Once we've crossed the discontinuity, the value of h gets larger again. So notice what's happening. This is more or less identical, as we would expect. As we approach the discontinuity where we switched off the voltage, we now get a different behavior to the solution. If we focus in on that discontinuity, we can see that h is getting smaller by a factor of 2, and then it gets larger by a factor of 2 until it's back to the usual size. In fact, we can take diff of t, the output vector of t's, and we can see what the h values are. H is about 0.2, except when we approach the discontinuity. In this case, the value of h plummets. Here it had to divide 2 by 2 twice, and then it kept on dividing by 2. After it crossed over this discontinuity, the value of h went back up again to about 0.2. So at the discontinuity, we let h be very small to try to avoid as much error as possible, and then h became larger again. You can even plot the value of h on a logarithmic scale, and again you can see we just keep on dividing h by 2, and we go back up again dividing h by 2. Let's try a sinusoidal output. So let's say, or the forcing function, let's say the forcing function is sinusoidal. So we have an input voltage times sine of 10 volts, times sine of 10t. Well, sine of 10t, we can just implement it in Matlab as follows. And now we can call dp45, plot it from 0 to 20, and as you expect, we get an output function that is also sinusoidal. So up until now, we've looked at finding solutions or approximations to solutions to a system of n first-order initial value problems. We then saw how we can take a second order or an nth order initial value problem and convert it into a system of n first order initial value problems, and then we use this exact same tool. There's just one other subtle difference thing we have to approach, and that is systems of second order initial value problems. So let's say we have n functions that are unknown, and we know that the second derivative of each of the functions is a function of time, of the first function, the derivative of the first function, the second function, the derivative of the second function, the nth function, the value of the nth function, the value of the derivative of the nth function. In this case, we need 2n initial conditions. We need to know the initial state of the first function, but we also need to know the initial slope of the first function. We need to know the initial state of the second function, plus the initial value, the initial slope of the second function, and so on and so forth for all of the n derivatives, or second derivatives. Well, in this case, we're going to do exactly the same thing. We're going to define a vector of w functions that are unknown, which we will try to approximate. And w1 is just y1. w2 is the derivative of y1. w3 is y2. w4 is the derivative of y2. w2n minus 1 is just yn. w2n is the derivative of yn. Note the error here, this should be a 2. I'll fix that in the slides. Now we have the derivative of this vector valued function, and again the derivative is given as follows. But wait a second, wasn't that equal to W2? And wasn't that equal to W4? Not only that, wasn't the derivative of the first function just F1? Wasn't the derivative of the second function, so this wasn't the second derivative of the second function just the function F2? So now we have a sequence. Here we have W2 and the right hand side of the first second order ODE. We have W4 and the right hand side of the second order ODE. So for example, here we have two very simple second order ordinary differential equations. I will just rewrite this as 4 first order initial value problems. W1 prime is equal to W2. W2 prime is just the right hand side here. Y1 is W1. The derivative of Y1 is W2. Y2 is equal to W3. The derivative of Y2 is W4. Similarly, the derivative of W3, which is Y2, is W4, or its derivative. The derivative of Y2 prime is the right hand side here. And so now we just have a sequence of steps. So if we approximate this solution, notice that the first row is Y1. The second row will be the derivative of Y1. The third row will be Y2, and the fourth row will be the derivative of Y2. Now I've only plotted Y1 and Y2 here, but you can see whether or not yours works as well. So we've looked at using the Dormand Prince method, and in fact you could use any method. We've looked at how we can take and solve, or at least find an approximation to the solution of n-coupled initial value problems. And we've also seen how we can solve or approximate solutions to higher order initial value problems. We saw that we can convert an nth order initial value problem into n first order initial value problems. We also saw that we could convert a system of n second order initial value problems into a system of 2n first order initial value problems. We saw both time varying and non-time varying solutions. So, good luck with your lab, and have a good day. Cheers.